Last time I announced our test was going to be on Thursday, the 21st. Did Magdalena tell you when her test is going to be?
Yes.
It's not going to be the same day, right? Okay, so we got that cleared up a little bit. I didn't say anything about what kind of questions you might expect for the exam, and it's a little hard to give you a whole lot to go on. Other than that, I would say know the pages of the notes, because I'll try to take questions that are like things that are in the notes. So I might be following some examples that are there. I might be following some kind of model that's there, that you have to do something similar to what's in the notes. I might ask you to do a small proof of something that's in the notes, so don't ignore that type of stuff as well. I'll give you some kind of computer output, either SAS or Minitab or something like that, but be prepared to do hand calculations. So I might give you partial computer output, and you have to finish it off with some hand calculations. So be ready with hand calculations as need be. Okay? Well, let's see. Today we have sort of miscellaneous kind of things to talk about. I'm trying to remember.
Doctor, I have a
Yes.
question, please. Can we use a formula sheet?
Oh, yes, thank you for mentioning that. You can bring one sheet of notes for the test. Write on both sides, whatever you want to write, so you don't have to memorize that much in the way of formula. So bring one sheet of notes for the test. Is the 30, so we have 2 observations per cell. So 2 observations per cell. All right, let's look a little further. So now we have some GLM output. The overall F-test, which I won't worry about here, but now the details are down here a little more. And so we have fertilizer main effect, soil main effect, fertilizer by soil interaction. And here's the F statistics and the corresponding p-values. All right. Now, what am I trying to look at here? I'm trying to look at what's the denominator in these F statistics. So for the interaction, general rule is always test interactions first, and then go on to test main effects after that. So anyway, I'm going to test the interaction first. I see the F statistic is 0.5, but that would be the mean square of 1.84 divided by the mean square error, which now I've crossed out, but it's right there, 3.66. And 1.84 divided by the 3.66 looks like about 0.5. So that's the F ratio here. It's mean square, let's call it AB, divided by mean square error. Now let's go up and look at soil, which is the random effect. And so I see an F statistic of 2.57. Where does that come from? Well, the mean square for soil is 9.41. So if I take the 9.41 for that mean square and divide it by the mean square error, 3.66. It looks like I'll get 2.57. I'll just assume that it comes out that way. So the test for soil is mean square, I guess I'm calling it mean, divided by mean square error. And then lastly, we come to the F test on fertilizer, which is the fixed effects in this problem. And it's 9.45. Now that's supposed to be a 34.63 divided by something. And
The MSE again.
pardon?
It's the MSE again.
It's got to be MSE again. Because that's about right. So it looks like that F is mean square A divided by, again, mean square error. Now, let me go back to an earlier handout about mixed models. Here it is here in my papers. Here it says 2 random factors and mixed models. So I want to look at the mixed model part of this, which is there, starting on page 6. Now, in this mixed model layout here, A is fixed and B is random. Okay, so here's the model. A is fixed, B is random. Okay, so here's the assumptions about the model. And I want to look at the over table. And what I want to start noticing is that, reading up from the bottom, for the interaction A, proper denominator is mean square error. For the random factor B, proper denominator is again mean square error. But, sorry, this is split across 2 pages here. For the fixed effects A, the proper denominator is the interaction AB. So this is what we had in our an overtable for the mixed model. Now, so I wanted to remind you about that. And so coming back to this current example here, I guess I would just simply say this one is wrong. Now, I don't have for me to look at or for you to look at either the SAS code that produced this output, so that's kind of awkward. But anyway, somehow I have to tell SAS which factor is random in the command somehow. And you can't see that because I'm not showing you the command file for this output. So anyway, I just want to point out with this example, on checking these F ratios, it's got the wrong F ratio for fertilizer, a fixed effect. And so it needs to be cleaned up and changed. So then the commands must go on and do t-tests for yield is our response. And so here's the stuff about t-test using the LSD method. And so we come over here. I'm noticing in here that it's telling us standard errors and probabilities calculated using the type 3 mean square for interaction as the error terms. But that's what it's supposed to do. So how does it know to do that when it didn't do it on the previous page? I'm kind of confused as to what went on the previous page. But anyway, maybe when I got to this part in the commands, I had somehow indicated a random factor in there, because this is what it should be doing. So anyway, we have the 3 means, and then we're going to do pairwise t-tests, and these are the results here that come out from those pairwise t-tests. They're all significant. Significant, significant, significant. Well, I can't really check this in class very well, but I'll just take the program's word for it. But this is what it did for the denominator. Okay? And that should be the correct thing to do for the denominator there as well. Okay, so not a very good example, but I thought it might be of some use to briefly consider it as well. Let's go on to something else. Example. Let's see what we've got going on in this example. So this is in Minitab. I have 4 columns. Columns for 5 dentists. Let's call that factor A. I have 3 methods. Let's call that factor B. And that's in the second column here. Then there's 2 types of gold. Let's call that factor C. And that's in the third column here. And then finally the response is the 4th column, the hardness of gold fillings. So somehow this is a dental set of data dealing with gold fillings. And you can see the size of the experiment. It has 5 dentists, 3 methods of probably doing the filling, and 2 types of gold. And so we have this data. Now, I think in this experiment I want A to be a random factor because I don't care about these 5 dentists directly. They're just 5 dentists that were selected from some available population of dentists, and so that's a random factor. B is the method, that's got to be a fixed factor. And then C, type of gold, 2 types of gold, that's got to be a fixed factor as well. So what you're seeing in this example is that now I have a mixed model with 3 factors. Our earlier handout only had 2 factors, 1 random and 1 fixed. Now this one has got 3 factors in it. So how does it work? Well, I'm going to cheat and let Minitab do all the heavy lifting. And so here's the command that I used in Minitab. I should have probably used GLM. I don't know what I was doing on this day, but it worked fine as it is. So anyway, what I do is to do, first of all, there's the response, the hardness. And then the model is here on the right side of the equality sign. And notice that I'm using the vertical bars. The vertical bars is the syntax in Minitab to say, take all the possible combinations, interactions here between 3 factors. So that means take the 3 main effects, take the 2-way interaction between each of the 3 pairs. So there's 3 2-way interactions, and then it also says take the 3-way interaction. Now if I make that the model, the command won't work. There's nothing left over for error, essentially, and so the command won't work. So what I have to do is to modify that by subtracting from that model this term. And you recognize that as the 3-way interaction term. Okay, so I'm subtracting off the 3-way interaction term to make this work. So that's a little bit clumsy, but it's what it is. So then I tell Minitab that the variable dentist is random. I should use the restricted model. I should show expected mean squares, and here's a plot which we can look at when it comes out. So anyway, what does Minitab do for us? Well, notice here it tells us that it's got 1 random factor and 2 fixed factors, which is what we want. So it's just kind of a double check that we can see the program is doing what we want. So then we get this ANOVA table here. Well, it's got the main effects, dentist, method, type. It's got the 2-way interactions, dentist by method, dentist by type, method by type. There's no 3-way interaction in this table because I took it out, right? So everything else is just lumped together into what the program is going to call error. And these degrees of freedom you can check are the appropriate ones. The 2-way interactions are the products of the degrees of freedom for the main effects and so forth. So we have sums of squares, we have mean squares, and we have F statistics. What are these F statistics? Where are they coming from? Well, let's turn the page. Somehow we've got to know what's the right denominator to use when we've got a random effect in this model. So on the back side of this page, you see Minitab's layout. And it's fairly self-explanatory if you just look at it. It says, well, here's the terms in the model again, over here on the left. It talks about variance component, which we can come back and talk about again in a moment. And it talks about the error term. Now let's take a look at this expected mean square column. So we'll start at the bottom. The error, we don't need to test about error. So we can say 7, the error, is the right denominator for that one, and for that one. So far. So the mean square error is the proper denominator for those three F statistics. Let's just take a peek on the previous page and see whether that's making any sense. It's hard to tell, these numbers aren't easy to spot. Well, if they're not too hard, the mean square error is 11,000 something. So if I divide that into 31,000, I get a little less than 3, which is the F. If I divide that small mean square by that, I get something rather small, maybe 0.2. And if I divide that one by 11,000 something, I get a little less than 1. 0.93 seems reasonable. So anyway, I think the program did the right denominators that it's telling us it's doing, and it computed that work there. So let's go on a little further then. Suppose I want to test type of goal. So here's the expected mean square. I have to find something that has the right denominator. So I've got to find something that has this 7 plus 3 times 5 as its expected mean square. And I see it right there. And so I would say that's dentist by type. So the proper denominator here would be mean square dentist by type. And notice how easy this is. If you have the list of expected mean squares, you can just look at it and just pick it right out. What's the right denominator? There's no detailed considerations to matter. So let's move up to the next one, the one about method. So we look at the expected mean square, and I have to find a denominator that has this expected value, 7 plus 2 times 4. Well, I look down at my list, and I see there it is. It's the interaction between dentist and method. So that one should have denominator, mean square, dentist by method. So let's go back and check the ANOVA table to see whether that's what's going on here. Let's see here. So we're talking about what's the proper denominator for type. Well, so there's the mean square type. What denominator do I want to use? I want to use, well, there's the mean square type in this column here. What denominator do I want to use? I want to use, I think, dentist by type.
Yep.
Okay. So take the ratio of those two, and it looks like I'll get something about 0.48. So it looks like the program is doing the right thing there. Now, coming back to where we were here, let's see. We had been talking about testing method, and the right denominator should be dentist by method. So they're testing method, there's its mean square. And the denominator should be dentist by method, which is this right here. So the ratio of those should be, a little more than 2. That looks like about right. Anyway, you can check those numbers out with your calculator, and I'm sure that they're going to match out as they seem to. So there's the denominator for that F-test. Okay. Now there's one more F-test here. Let's see where we're at. testing about dentist. That's the random effect, right? All by itself. So we look at this expected mean square here, and we see the proper denominator would be 7, just the mean square error. So this is simpler than the other ones were. So the proper denominator for dentist is 7, the mean square error. So if you look back here on this side, for a mean square at 17,000 something, the mean square error is 11,000 something. Dividing those out, we would get 1.53 is about right. Somewhere between 1 and 2 would be where the answer would lie. So there's how we would figure out the F ratio with a test about dentist. Well, what this example starts to show you is that if we go back to my earlier handout on mixed models, this one, 2 random factors in mixed models, when we got into the mixed model part, we only had 2 factors. If it's going to be a mixed model, one of them is going to be random and the other one is going to be fixed, and there are no other choices. That's it. So that's what this handout is dealing with in a way. Factor A is fixed and B is random. If we have more than 2 factors, now there are more possibilities that can arise. If I have 3 factors, for example, one could be random, the other 2 fixed. 2 could be random, the other one fixed, and so on and so forth. So there's different ways we can have mixed models. If we start to have more than 2 factors, it gets complicated. Okay, now. Well, I forget the source of this handout off the top of my head. But anyway, I found this algorithm for rules for setting up the expected mean square column. And so it tells us in a fairly direct way what to do. Step 1, do that. Step 2, do that. And there's step 3. And those are easy. Step 4, step 5, and the tricky one is step 6. But there's 6 steps here, and this is going to an example to illustrate these steps. It leads us to an answer that looks like this, and in particular, what it has in it is this column of expected mean squares over here. So, the purpose of this handout is to show you the algorithm for, I guess, the hand calculation of the expected mean square column. Follow this routine. So, I guess the way this is written, it's an example already. So let's begin with step 1. So apparently we have a model with 2 factors, A and B, and the model contains an interaction, AB, and an error term. Notice in the way this handout works that in the error term, they write it that way. So just notice that. Right? So that's the first step, just to make a column of the terms that are in your model. Simple to do. Okay, so those are the terms we wanted to run. Then go on and figure out this stuff on the top here. So basically, we label the subscripts I, J, and K, and over each subscript write F if the factor is fixed and R if it's random. Well, apparently the way this is working, A is fixed, B is random, and then if A is fixed and B is random, then the interaction is going to be random as well. So we have that. So notice that in this example, A is fixed and B is random. And then finally on the top, put the sizes of things. Put the number of levels for factor A, which is little a, the number of levels for factor B, which is little b, and then the number of replications per cell, which we've called little n. So this is matching the notation of our handout as well. So fill those in there, and we're done with step 2. Now it says for each row, copy the number of observations under each subscript, provided the subscript does not appear in the row heading. So in each row, we're supposed to put some numbers. Well, in the first row, labeled AI, we don't have anything from this first column because that's got I in it. So we're supposed to do this provided the subscript does not appear in the row heading. So this row heading has an I in it, so we don't do anything with the first column. And we come over here with the second column, and there's no I in there, and so we write down a B. B is the number of observations under each subscript. So little b is the number of levels for factor B. And then we do that over here on the last column, the column for K, and we pull down an N for that. Each cell has N observations in it. So we've done the first row. Now in the second row, we do the same thing. We're looking at a row labeled BJ. So we come to the first column here, and we pull down an A because that's an I. We come to the second column, nothing is pulled down because that's a J. And it says up here, provided the subscript does not appear in the row heading. So we don't drop anything down for the second column, we leave it blank. Then we come to the third column, and there's no DJ with no K in that, so we pull down an N there. And so we're done with the second row. Now we come to the same consideration finally for the next row on interaction. ABIJ. Do we pull anything down from the first column? No, because there's an I in this term in the model. Do we pull anything down from the second column? No, because there's a J in the term in the model. Do we pull anything down from the last column here? And you see we pull down an N because there's no K in this ABIJ business that's here. So we have that. And the last row is totally blank because we can't pull down anything from the I because there's an I in there. We can't pull anything down with J because there's a J in there. And we can't pull anything down with K because there's a K in there. So the whole last row is blank. All right. Then step 4. For any parenthetical subscripts in the model, place a 1 under subscripts given in parentheses. Now parentheses are going to be important for us when we start talking about nested designs. It's the standard notation for describing nested statistical designs. We haven't talked about nested designs yet, so the only thing we have with parentheses in it is this error term, the epsilon k parentheses ij. So anyway, let's take up our story where it was at and follow this description. For any parenthetical subscripts in the model, place a 1 under the subscripts given in parentheses. So we're looking at this epsilon k I j. I is in parentheses, so put a 1 in that column. J is in parentheses, so put a 1 in this column. K is not in parentheses, so nothing is done there. Done with that. Fill each remaining cell with a 0 or 1, depending upon whether the subscript represents a fixed or a random factor. So let's see here, what am I doing? I have a 0 there, because that's a fixed factor. And let's see, the second one in the second row is a 1, because that's a random factor. And what else are we adding in here? Let's see. Oh, the interaction, 0, 1.
So what do you have a 1 on the interaction?
Pardon?
Why do we have 1 on the interaction? IJ.
I haven't got that far yet. Hold on. I'm still trying to think about what's going on here myself. I'm looking at this interaction row, and up here I have nothing in the interaction row, in the first 2 columns anyway. So now I want a 0 and I want a 1. It says, fill in the remaining cells depending upon whether the subscript represents a fixed or a random factor. Well, we have any ij. I is fixed, so I'm going to put a 0 in that first column. J is random, so I'm going to put a 1 in the second column, and so I have that. Then I finally come down to the last row, the error term, and the only thing that's left open is this lower corner entry here. And I guess the error term is always random, so we've got to have a 1 there. So now we've got all this table filled out. Now how do we use it? It says to find the expected mean square for any term in the model, cover the entries in the column that contains non-parenthetical subscript letters in this term. So let's see what that says. Let's see, for AI, cover column I. Well, if I'm looking at this, I don't want that way. I'm going to cover column I. Oops, so I'm going to cover it without blocking this off. And then it says, multiply the remaining numbers in each row. Each of these products is the coefficient of its corresponding term in the model, provided the subscript on the term is also a subscript on the term whose expected mean square is being determined. Now that's messy to interpret. So anyway, I think the way this goes is I have to cover column I. I'm looking at row AI. and multiply the other two numbers together, b times n, and that comes over here as the coefficient of the A burn, En VA. But there's more, so cover the entries in the column that contain non-parenthetical subscript letters in this term. Oh, this is just hard to talk about here on the board, pointing my finger. So this being awkward, let me just stop this discussion at this point. What you're supposed to basically do is to follow this prescription here and the numbers that are in here and use these to produce these expected mean squares. The expected mean squares involve two things. Which terms are there? Sigma squared, which terms are there, and then what are the coefficients, n or the na, and so forth. So those are the things we have to identify from this information that's over here. Now, as an exercise, go back to this gold fillings data that we talked about earlier today, which had three factors. Write out the terms of the model, which you can kind of see here in the ANOVA table, and show by using the method of the handout that these are the right expected mean squares that MeanCat is giving us. So in other words, be able to produce this column of expected mean squares by hand. That's your job. So do that as an exercise. You've got the answer and what you're pointing towards. So see if that comes out okay for you on checking that out. All right, so here's some data, as it says here, on this yield of a chemical process. They were studying pressure and temperature, each at 3 levels. Only 9 runs could be done in a day, so for replication, the experiment was repeated on the second day. So we have day, first day, 9 observations, second day, 9 observations. Then we have pressure at 3 levels. We have temperature at 3 levels, there they are, and here's the yield of the process response variable over here. So I want to test whether or not pressure or temperature is having any influence on the response. I've got 3 factors, day, pressure, and temperature, but I'm not really interested in the day as an important factor. It's sort of like a blocking variable. You know, I sort of ran the experiment in 2 blocks. First block, 9 runs. Second block, another 9 runs. And I presume one could have done time was available. But anyway, it looks like we have three variables, but one, day, is only a blocking variable. I'm not really interested in any inherent way. I'm mainly interested in the other two, pressure and temperature. So how might I do this? Well, you can already be reading ahead, see that I'm going to use again the same command that I used in the previous example. Here's my bonds, all the combinations, I take away the three-way interaction, maybe that, and so, I mean, you can, this is a little awkward because it's referring to C's rather than names, right? This is C1, this is C2, this is C3, this is C4. So that's where these columns are coming from. Random date. So I look at these three factors, and I said the only one that's random is the black one, the date. The other two variables are inherent in the nature of the business, the pressure, the temperature. Those wouldn't normally be random at all. So those are fixed. A day, random. I don't care about any particular days, but I have to do some days in the experiment. So day is a random factor. All right. Day is random. Use the restricted model. Give me the expected mean square column. And then get the means of the response broken down by pressure and temperature. Should have gone to use those or something. So many tabs and over gives me some basic descriptive stuff. It lists the factors that it's dealing with. One is random, the other two are fixed. Number of levels of those factors, and then here's the table. So if we look at this ANOVA table and just quickly do the F-tests without worrying about where they're coming from yet, start with the interactions first. So this one is significant. This one is significant. That one is not. And then that main effect is significant. Pressure is not. Day is significant. So day might be a significant factor, but I don't really care about that because day is just kind of a nuisance for me, right? Now, I haven't emphasized this point to this class enough, I don't believe. But basically, when you have all these possible F-tests to run, you should test the interactions first. If you find significant interactions, do not go on and test main effects because they don't mean anything. So in this example, for instance, I'm finding there's an interaction between pressure and temperature. Those are the two main variables of interest for us. So I'm finding this interaction here. And so when I would look up here and say, here's two tests about the main effects of those two factors, I would say throw those away. They don't mean anything. You can't interpret them. Let's say it another way. So anyway, that's happening in this example. I'm not trying to make a big point about it, but just a small point about the order in which you do the testing and do you do all the tests that are available to you when there are so many to do. Well, I had asked for an interaction plot, And he gave me this stuff here. Now we have found a significant interaction between what again? Let's look. It was between pressure and temperature. So these last two variables here, there's a significant interaction between those two. So here's the interaction plot one way, and here's the interaction plot the other way. They're both plots of the same exact data. But you notice to your eye, they don't appear to be the same, do they? Right? So that's just a little warning to us to be careful about plots. The scales and so forth are chosen for us, perhaps, and we don't have any control over that. So anyway, these two plots, I want to repeat that again, are plots of exactly the same dying beam, this one and this one. And so they're identical information in these two plots. And what we're supposed to say basically is that these profiles are not parallel. No interaction means these profiles should be parallel, but they're not parallel. They're just a little bit off, and that's why we're finding a significant interaction. Now, a researcher might look at this and say, well, yeah, they're not parallel, but they're not too far away from being parallel. Maybe I can just ignore this. Assume they're parallel enough, so ignore the interaction that we're finding. That may be something a researcher chooses to do. But anyway, the main point is to just remember that this plot and this plot are exactly the same information. Now, then we go on to the next page where we see Minitab has produced the expected mean square column. And we can read this in the same way we did the previous example. So if I want to know what's the right denominator for this interaction, I can say it's 7. For this interaction, it's 7. For this interaction, it's 7. For this main effect, I've got a denominator whose expectation is 7 plus 3 times 5, which is right there. So there's my denominator for that test. And then I do the same thinking for the second. And when I come up to the top one again, I have just a 7 here, so the mean square error would be the denominator for that one. So anyway, in a simple way, we identify what are the proper F ratios by looking at the expected mean square column. Now you notice in the Minitab command that I used here, and in other examples that I've used before today, I've got this subcommand of restricted. I'm telling Minitab to assume a restricted model. So I did it again here. Now what I want to do in this output is to just see what happens if I take that away. So here's the same ANOVA command. Random day, expected mean squares, but take out that restrict. In Minitab, that's actually just a little check box in the menu, so just uncheck it is all I did, and then run it again. So anyway, here's the Minitab output for the unrestricted model. And let's see, try to wrap up this example quickly here. What you see is different F-tests because these expected mean squares are not the same as in the previous case. There's some similarities, but other parts are different. So what the program is going to use these to build the F ratios that are here. Then what it did was to say, and we'll have to talk about this in another next time as well. It put an X by this first one, and it said, well, how do I test this first variable? I've got to find the denominator, which would be 7 plus 3 times 5 plus 3 times 4. And I look at the possibilities that I have, and it's not there. Right? So basically, we've got to do some trick to figure out how to build a denominator for that case. We don't have time to talk about it today, so let's just leave this example at that point, and we'll pick up that matter next time.